Oxidation numbers. With oxidation numbers, your life becomes a little bit easier if you just understand a couple of shortcuts. So these shortcuts usually involve compounds involving polyatomic ions, because these are the ones that the charge gets a little bit interesting. So what you usually should do is separate the ions. So K we know is a positive 1 because it's group 1. NO3 is negative 1 because that's what the charge on nitrate is. You could also uncrisscross, which is basically, since there's 1 NO3, you figure out the charge that the potassium had to be a 1. And so there's 1K, you figure the charge on NO3 had to be a negative 1. Either way, you get the same result. So by separating it, I figured that potassium is positive 1. So on top, I put the charge overall from that ion, and then I divide by whatever subscript is here, which in this case is a 1, and I put the actual individual ion charge as positive 1. They're the same number because there is no subscript here, meaning that you just have one potassium and that's its charge. The reason I do this is for counting purposes. The bottom number is really what I'm interested in. The top helps me get those numbers. So let's take a look at nitrate. Alright, so between these two, which one do you know a charge for? Well, according to oxidation rules, you know the charge on O. Each O is a negative 2 charge. There's 3 of them, so multiply 2 times 3, you get negative 6 charge. Alright, now the charge of nitrogen has to be such that the overall charge in this polyatomic ion is negative 1. So what does it have to be? It has to be a positive 5. That's positive 5 and negative 6 gives you negative 1. So dividing it by the subscript, which turns out to be 1, gives me a charge of positive 5. So those are my charges. So positive 1, positive 5 for nitrogen, negative 2 for O. And that's what I would be using to figure out if it's oxidation or reduction. Let's try another one. Same thing, I'm going to take ammonium, NH4, separate it, do the same thing with nitrate, minus 1. Now I'm going to figure out the charges. For this one, it's very important because you have two N's. How in the world would you figure out the charge of each N unless you go through this process? Well, you'd have a pretty hard time if you did try to do it any other way. Alright, H we know anytime it's in a molecular compound, it's a positive 1. So each H is positive 1. We have 4 of them. So the overall charge from H is positive 4. What's your charge of nitrogen have to be? Well, what number plus 4 gives you positive 1? That would be a negative 3. So I figured out this is negative 3, this is negative 1. Alright, now I'm going to go to NO3. I know O is negative 2. There's 3 of them, so negative 6. What does N have to be here? Positive 5. That's a charge on nitrogen. Should have brought it down over here too. So this becomes a positive 5. This becomes a negative 2. And we're done. Alright, same thing with here. Now, in this situation, you have hydrogen, carbon, oxygen. You really don't need to separate it out unless you just want to get more practice with it. So I'm going to do it without separating it out. H, I know this is going to be a positive 1. There's 2 of them, so positive 2. O, we know is a negative 2. There's 3 of them, negative 6. So what does this carbon have to be in order to make this charges match up? Well, minus 6 plus 2 gives you minus 4. So this has to be a positive 4 to make the charges balance out. And you're done. Alright, same thing with this one. I don't really need to separate it out, so I'm not going to. The ones you really have to worry about separating out are the ones involving 2 polyatomic ions or a transition metal and a polyatomic ion. So for this one, I'm going to do the same thing I did for, let's make sure it's pencil. Alright, so for O, each O is negative 2, so that's a total of negative 8 charge. K, we know is positive 1, because it's group 1, so that's overall positive 3. So what does P have to be to make this work? Well, the compound has to be neutral as a whole, so P has to be a positive 5. So positive 8 versus negative 8 gives me an overall charge of 0. That tells me I did it correctly. Alright, this one. Alright, you have 3 nitrates and you have an aluminum. So I'm going to separate this out. You don't really have to, but just to show you that you could do it both ways. It's 3 plus. I just took this 3, put a charge of aluminum. In case you forgot, aluminum is always a positive 3. And Same thing with nitrate. Alright, so aluminum we just figured out as positive 3, so I'm going to put positive 3 in the bottom. O, negative 2, as always, gives me a negative 6. Remember, the only time O is not a negative 2 is in peroxide. That's about it. Alright, N has to be a positive 5 to make this whole thing work. So, positive 5, negative 2, and I'm done. Notice the 3 didn't really factor in me figuring out the charges. And if you crisscross it, you avoid some of the mistakes that could happen if you kept it as was. So, it's whatever you're comfortable with. Alright, this one, definitely going to break it apart. So, NH4, positive, SO4, 2 minus. Alright, I'm going to first handle the nitrogen, the NH4. So, we know each H is positive 1 because it's a molecular compound. Give me an overall charge of positive 4. So what does N have to be to make this work out? Negative 3. So negative 3 plus 4 gives me a positive 1. Same thing with this. Negative 2, there's 4 of them, so negative 8. What does sulfur have to be? What plus negative 8 gives you negative 2? That's right, positive 6. Alright, done with that one. Alright, now we're going back to a compound that does not involve 2 atomic ions. So I'm going to deal with it as a whole. So K is positive 1, 2 of them. O minus 2, 7 of them. So what does this have to be to make this work? It has to be positive 12, because 12 plus 2 is 14, and 14 minus 14 gives me 0. So what's the charge on each chromium? 12 divided by 2, positive 6. And once again, these are the numbers I'm really interested in. This is for counting. This is what we want when we're figuring out oxidation and reduction. Alright, KMnO4. Same thing. We'll do K, do the whole thing together. O, negative 2, 4 of them, negative 8. So what does manganese have to be? Positive 7. It's positive 7 plus 1 is 8, and negative 8 gives you an overall charge of 0. Alright, so now let's take a chemical reaction involving redox to show you how this whole oxidation reduction thing works out and how you identify things. Alright, so which one of these would I deal with first? Well, sulfide usually is a negative 2. So I'm going to deal with sulfide first. It's better odds. There is no rule for sulfur, there's no rule for arsenic. So you go for the one that's the most common as far as charges are concerned. That's usually your, group 15, 16, 17, which is negative 3 for 15, negative 2 for 16, and negative 1 for 17. So we know sulfur is a negative 2, so that gives an overall charge of negative 10. So what does the overall charge in arsenic have to be? Positive 10. And we divide that 10 by 2, we get a positive 5. And once again, these are the numbers we're really interested in. This is positive 1, tells us, makes your job easier. Alright, this, negative 2, 3 of them, negative 6, nitrogen, positive 5, only 1, so positive 5. So once again, H, molecular compound more or less, so we're going to plus 1. Arsenic is a metalloid, so that's why you could get away with that. If this was, sodium hydride, where hydrogen is reacting with a metal, then you couldn't do this. Overall charge is positive 3. Oxygen, negative 2, 4 of them, negative 8. So what does arsenic have to be to make this work? Positive 5. Alright, we're going to do all of them, and then we're going to come back and see what oxidized and what reduced. Alright, for this one, you have negative 2, 4 of them, negative 8. So what does it have to be? Positive 6. Because positive 6 and negative 8 gives you a negative 2. H2O, negative 2, negative 2, positive 1, 2 overall, so charge is 0. So the top number should equal up to whatever the overall charge is, whether it's negative charge or no charge, it should balance out somehow. NO2, 2 of them, positive 4, positive 4. Alright, now look at it. Alright, arsenic went from positive 5 to positive 5. It's not doing anything. This is not your oxidation, not your reduction, so we ignore it. Sulfur, it's going from negative 2 to a positive 6. So I'm going to draw a line connecting these two to show that this is actually, bad arrow, that this is actually going to be a -2 to +6 is going to be oxidation. It's becoming more positive. Alright, and what's being reduced? Well, you see nitrogen is going from a 5 to a +4. There's your reduction. So the rest of the chemicals are just there. Their charges don't change, so they're not being oxidized or reduced. So the ones we really care about is the N and the S. And that's what we would pay attention to in case we have to figure out what the oxidizing agent was and what's the reducing agent. Just to point this out real quick, since this is being oxidized, this compound is your reducing agent. Since this is being reduced, this is your oxidizing agent. Alright, let's try this other one. Same concept. We know O is -2. 3 of them, so -6. That makes this a +6. 10, +2. Work done for us. +1, -1. We're done with that. Alright, so here it's a -2. So it's a -16. It has to be a +16. And this is where it gets kind of weird. Because 16 divided by 3 is 16/3. How's that possible? Well, sometimes you get some really weird oxidation reduction reactions, especially ones that are just there to kind of challenge your ability to balance. So just understand in this situation that something's fishy going on. More than likely what's probably happening here is that the person that wrote the question probably, didn't check this out. So you usually don't get fractions, but anyways, we'll just assume that this works and we'll go with that. Chloride, same thing. We'll go with a -1. There's 6 of them, so -6. 10, +6, +6. O, -2, -2, +1, +2. Alright, so what's happening? 10 is going from a 2 to a 6. So there's our oxidation. And what's being reduced? H staying the same, chloride staying the same, O staying the same. W is the one that's going a little weird. It's going from a +6 to a 16/3. So just for the sake of argument, we'll say this is our reduction. And understand that on the actual AP exam, they're not going to get cute like this and try to do fractions. They're going to give you whole numbers. But just for the sake of argument, that's how you identify oxidation reduction, and that's how you figure out charges.